Right, welcome back. In this segment, as promised at the end of the last segment, we are going to apply our newly gained ideas of objectivity to understand more about restrictions on constitutive relations for solids. Okay, we'll spend the next segment or two focusing on solids, maybe even 3 segments focusing on solids, and then proceed to fluids. Okay, so the topic of this segment for certain is objectivity of hyperelastic strain energy functions. Okay, so here is the picture. We have our solid body in its reference configuration. It already has been deformed into a current configuration. Let me draw a current configuration that I am able to show a rigid body motion on. Okay, so current configuration, omega sub t, spatial position of a material point, right, little x, and now we have a superposed rigid motion. Right, not so bad, looks reasonably rigid. Okay, so we'll denote this configuration, omega t plus perhaps, and we will denote the position of the material point, the new spatial position, as x plus. All right, now if this is phi, we know that this is what we have been denoting as phi plus. Okay, and we have a rigid motion, right? So what we have is rigid body motion of the current configuration right, config as short for configuration. So rigid body motion of the current configuration from omega sub t to omega sub t plus. Okay, so it's that last part of the motion that is rigid. And what we've seen is that we can then write phi plus as consisting of a translation vector, function of time, plus a rotation, which is written as the action of an orthogonal tensor on the spatial position. Okay. Okay, so Q is an orthogonal tensor with a positive determinant equal to 1, in fact. All right, so this is the setting, okay? And also, to recall, we've done this many times, but no harm doing it once more. Reference configuration, current configuration deformed, and now a superposed rigid motion on that current configuration. All right? Here's the question we want to pose. We are saying that from the reference to the current configuration, there is in general a deformation. I don't know if you can see it, but I'm squeezing the ball. Okay? So there is a deformation. There is energy stored now. There's a strain energy, right? Because we are working with hyperelastic strain energy functions, we have this strain energy density function. All right. and then we do a superposed rigid motion. Okay, so now this motion is rigid. Okay, so there is energy stored in the body, strain energy stored, but that strain energy came about from this part of the motion, right, of the deformation, from the reference configuration to what we may call the initial current configuration, omega sub t, in our figure here. All right, so there is energy here. And now the question we want to ask is, what happens to that strain energy density function as we go through rigid motions from here to there? Okay? So let's pose this now. Okay, so we have a strain energy density function okay, which we've agreed to call psi. It's a scalar, and we've seen that because of this intuitive physical idea that energy is stored as a function of the deformation gradient, we have that parametrization. Okay, so we have the strain energy density function, which is a mapping from right, the space of general linear transformations in 3 dimensions to scalars, right? It's a scalar function of a tensor argument. Okay, so we have this, and what we're saying is that that is the deformation gradient, right? For the deformation that takes us to omega t. All right, and now for the superposed rigid motions, we are asking, well, what should happen to psi? Okay. Now, psi, of course, is a scalar. It's a scalar function. And so as we saw in our discussion in the previous segment, this function should essentially remain unchanged under superposed rigid motions on the current configuration. Okay, so we have f plus then, right, which is, we've seen already, it's, well, this is the definition of f plus. Right? And we saw previously that this is now given to us by q, function of time, acting on f. Okay? All right. Fine. So we have this happening to the deformation gradient, and the question we are asking now is what should happen? So the question we are asking is, what about psi? Okay, so what we observe is that psi plus, okay, which will be evaluated with f plus, okay, right, should be equal to psi, which is evaluated at f. Okay, this is the condition, and this happens because psi belongs to R, right? It's a scalar. All right, and we saw last time that essentially scalars do not change under rigid motions. Okay, and the physical notion is very obvious here, right? The physical notion is that yes, we've deformed the body, there is an energy stored, but in going from this, so this is this energy density function now is psi, right, as a function of f, and f is the deformation from here to here, deformation gradient from here to here. We're saying that when we undergo superposed rigid motion, there should be no change in that strain energy function, right, and that strain energy density function, right? That's an obvious physical understanding of what it means to have rigid motions. Okay, so, right, and that essentially is what we've written, right, and the physical notion is that physical interpretation is that there is no change in strain energy or strain energy density due to rigid body motions. All right. Okay. But now what this implies is essentially what this is saying is that when it comes to evaluating our function, what we can write is that the strain energy density function in the state after rigid motion is obtained by just looking at our actual function and evaluating it with f plus. Okay? All right? And the requirement is that, well, it doesn't matter whether you evaluate that function with f plus or with f. Okay? It has to be the same. So what we're saying actually is something more about the function psi itself, right? We're saying that you need to pick a function psi that satisfies this. Okay? All right? Note that this has to hold for all points x, for every point on the body, right? And for all time t in our time interval of interest. Right, for all points on the body and for all time. Okay, so this of course implies that psi has to be such that qf psi evaluated with qf, because that is f plus, should be the same as psi evaluated with f. Okay, for all x, t, and importantly for all q, function of time, belonging to SO3. Okay? All right? Importantly, this has to hold at any position of the body, at any point in the body, at all times, and for any rigid motion on the body, right? So there's nothing special about the rigid motions that we apply. It has to hold for any kind of rigid motion, right? Importantly, for any rotation tensor. Okay. Well, what do we do from here? What we do is to recall the polar decomposition, specifically recall the right polar decomposition of the deformation gradient. Okay, and that theorem says that f can always be written as r u, where r belongs to SO3 plus, okay, and right, r always belongs to SO3 plus, implying that there is a rotation that does not change the handedness of any triad of vectors that we pick, right? And furthermore, that u equals u transpose, okay? And that u is positive definite, right? And the way we wrote, we combined symmetry and positive definiteness by saying that u belongs to a space of tensors which is given by S, right, for symmetry, and S3 plus, right? The plus there says that it's positive definite. Okay, and you recall all of this, right? So remember, what this leads us to conclude is that R is essentially a rotation tensor, right? And U is what we call the right stretch tensor. Right? Okay, remember these? Right, so U gives us the idea of how the material is being stretched in its principal directions. We looked at the eigenvalue decomposition of U, we looked at this notion of spectral decomposition of U, and so forth, right? Okay. Also note that because in general that deformation that we applied to get to the initial deformed state could be inhomogeneous, right? So the deformation was reference to current, and I'm squeezing the ball, right? Obviously not squeezing it uniformly, right? So that deformation gradient is in general inhomogeneous, right? Non-uniform. It can be a function of position, of reference position. All right. So f of function of f parameterized by x and t implies that each of our rotation and stretch tensors also are functions of reference position and time. They also can be inhomogeneous, right? Okay, so this is the setting we have. All right, so now let's apply this. Apply to the requirement that psi of q, function of time, f x comma t equals psi f x comma t. All right? Okay? So what this says is that psi q function of time r function of reference position and time u function of time equals psi. I'm going to write the right hand side as a function as depending upon f, function of position and time. All right? Okay, now remember, I'm beating this into you. For all x belongs to omega naught, time belongs to the interval of interest, and q belongs to SO3 plus. Okay, we have this setting. All right, so here's where I pull my tricks. I'm going to say that since I can do this this has to hold for all q, I'm going to play a game with you. I'm going to tell you, all right, now tell me at what point x and what time t you want me to apply my arguments. You pick a particular position on the body, right? You pick a particular position on the body. This is omega t. Okay, you pick, this is omega naught. So you say that I want you to apply it at that position x, okay? And you say that, well, okay, it goes to little x and it's at some time t. You say, okay, this is the situation under which I want you to, that you want me to apply my arguments, okay? I say, all right, excellent, you picked x and t, my turn now. At that point x, and for that time t, we've already written out the polar decomposition, right? We already have it here. Now I can apply my arguments for any rotation tensor q. Okay, I am going to, we have phi here. Okay, I am going to do the following. I'm going to say, well, choose q to be such that, okay, choose q function of time such that at the time of interest, okay, such that q, say t, okay, when I write t in this last line, I'm saying that t is the time of interest, right? On the previous line here, I'm just writing q as a parameterization in t, okay, as parameterized by t. So when I write t here, I'm saying that this is the time you have picked, okay? So I'm saying I'm going to pick a rotation which evolves with time such that at the time of interest, t here with the arrow, q is such that q equals the transpose of the rotation tensor at the point that you picked and the time that you picked. I'm at liberty to do this, right? And I can definitely construct q's that do this. All right? So what this implies then is psi r x comma t, sorry, r transpose, because that was the q I picked, r x comma t u x comma t equals psi f x comma t. All right. Now this of course gives me the isotropic tensor, right? Because R is an orthogonal tensor. Okay, so what does this imply for us? It implies for us that what it implies here is that psi, I'm going to flip the left and right hand sides, okay? I'm going to write what was the right hand side as the left hand side. Okay, psi of f at any position and time, remember you pick the position and time arbitrarily, is equal to psi, but now as a function only of the stretch tensor at the position and time of your choice. Okay, this holds for all x belonging to omega naught and t belonging to the interval of interest. Okay, so let's recall how this argument went. The body was deformed from the reference to the current configuration, and then we applied rigid motions, right? So to apply these arguments, I said you pick the position, the reference position, which means really the material point, and the time at which you want me to apply my arguments. You pick them, right? Maybe you picked that point and you said, okay, at that point at this time, okay? I said, all right, we've got to the state of deformation. I'm going to apply rigid motions, but now the particular rigid motion I will pick involves a rotation which coincides with the rotation tensor of that point at the time that you picked. Okay, well, it's not the it's the transpose of that rotation tensor. Okay, and what we see is that we conclude then for an arbitrarily chosen point x and time t, right? These are arbitrarily chosen by you, right? For that arbitrarily chosen combination, we see that this requirement must be satisfied on the bottom line. Okay? Now this was arbitrary, right? So you may say, all right, the function was special. It just turned out to be such that for that position and time, we need to have this argument satisfied. Fine, but then the function has already been set, right? Right? It's some function. We're just trying to find restrictions on it. I said, all right, go on, let's play the game again. You pick another point and time. We do the same thing. I apply a different rotation, okay, which now is the transpose of the rotation tensor of your newly picked position and time. Same conclusion. And over again, right, until we get tired. Okay? So note that x belongs to omega naught and t belongs to 0, t for this argument. Right, to make this argument, were chosen or can be chosen arbitrarily. Right? And it always has to hold. That relation psi function of f can only be dependent upon f through the stretch tensor. Always will hold. Right? We'll always reach that conclusion. Well, what is the only way in which we can always reach that conclusion? Okay? The only way that can happen is, this implies that psi depends on f. Fair enough, it does depend upon f only through the stretch tensor U. Okay, that is the only kind of psi we can admit if we want to satisfy this physical requirement, and well, it comes with a mathematical interpretation. This requirement that under rigid motions, right, of the deformed configuration, there is no further change in the strain energy. Okay, right. All right, but now we observe something, right? We say, okay, if psi depends only upon U, we see that it implies many other things, right? But we see that U, if we have U, then we can take U square, which is our right Cauchy-Green tensor C, right? Correct? Okay. Well, but then if we have U, as you can see, we always have C, and likewise we also have 1/2 U square, which is C now, minus the isotropic tensor equals the Lagrange strain tensor. Okay, so we've seen that this little argument we've carried out essentially implies that our strain energy function, which we agreed for a hyperelastic material can depend upon psi, must depend upon F. It is psi, it must depend upon F. We've seen that it can depend upon F only through its stretch tensor U. But then if it depends upon U, we can equivalently write it, because once we have U, we uniquely have C. We can always write it as some other function, which I've denoted as psi bar now, depending upon C. Or we can write it as yet another function. I will denote it as psi hat, function of E. Okay? So all of these are admissible strain energy functions. Okay? And all of them satisfy this requirement of objectivity, or as it is sometimes also referred to, the requirement of frame invariance. Okay? All these forms, okay, that is psi U, psi bar C, and psi hat E, satisfy objectivity or frame invariance. Okay, stated differently, they are rotation invariant. Right, we can take our reference configuration, our current configuration, and spin it as much as we like. No difference to the strain energy function.